Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 38, in which I will give the concept of Euler's phi function. Now I would like to give you an idea which will inspire you to know about Euler's phi function. Let n equal to 4. Now we find the positive integers not exceeding 4. Positive integers not exceeding 4 are 1, 2, 3, 4. Here GCD of 4 and 1 equal to 1. GCD of 4 and 2 equal to 2. GCD of 4 and 3 equal to 1. GCD of 4 and 4 equal to 4. Therefore, we get two integers 1 and 3 which are relatively prime to integer 4. Now we count number of these integers and write the number as 5, 4 equal to 2. Only we get two integers 1 and 3 which are relatively prime to integer 4, and this is called the Euler's phi function of 4 equal to 2. Now we take another example. Let n equal to 9. Positive integers not exceeding 9 are 1, 2, 3, 4, 5, 6, 7, 8, 9. Here GCD of 9 and 1 is 1. We are writing GCD below the number 1. GCD of 9 and 2 is also 1. GCD of 9 and 3 is 3. GCD of 9 and 4 1. GCD of 9 and 5 1. GCD of 9 and 6 3. GCD of 9 and 7 1. GCD of 9 and 8 1. GCD of 9 and 9 is 9. Now we count number of those integers whose GCD with 9 is 1. This number 1, 2, 3, 4, 5, 6. So we write 5, 9 equal to 6. This is called Euler's phi function of 9 equal to 6. Now we define this concept. Now we define Euler's phi function. Positive integers not exceeding small n belongs to capital N. Capital N be the set of natural numbers, that is set of positive integers as well as they are relatively prime to n, then number of such positive integers is called Euler's phi function of n. It is denoted by phi n. Here we see the term relatively prime to n. Positive integer relatively prime to n means GCD of that positive integer and n is 1. Also here given that positive integers not exceeding n means we have to take all those positive integers which are not greater than n, and if sum of the positive integers which are less than equal to n and their GCD with n is 1, that is they are relatively prime to small n, then number of such positive integers is called Euler's phi function of n. Here we see that small n is a positive integer. Therefore, domain of this function phi is the set of positive integers. Therefore, we may apply the concept of arithmetic function, multiplicative arithmetic function and completely multiplicative arithmetic function. Now we prove a theorem. Theorem is if p is prime, then Euler's phi function phi p equal to p minus 1. Given that p is a prime number, positive integers not exceeding p are 1, 2, p. Here GCD of p and 1 equal to 1, GCD of p and 2 equal to 1, GCD of p and p minus 1 equal to 1 and GCD of p and p equal to p. Therefore, we get that 1, 2, p minus 1 are relatively prime to p. Therefore, 1, 2, 3, p minus 1 are relatively prime to p. Therefore, number of positive integers not exceeding p and they are prime to p equal to p minus 1. Therefore, Euler's phi function of p equal to p minus 1. Proved. Now we prove a theorem. Theorem is if p is a positive integer with Euler's phi function phi p equal to p minus 1, then p is a prime number. given that p is a positive integer and phi p equal to p minus 1, this is number 1. If possible, let p is not a prime number. That is, p is a composite integer. Let d is an integer such that d is greater than 1 and less than p. D divides p. Therefore, GCD of d and p not equal to 1. Therefore, d and p are not relatively prime. Since d belongs to 2, 3, dot 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 p minus 1. Therefore, Euler phi function phi p is less than equal to p minus 2. Let this is number 3. Therefore, 1 and 3 contradict with each other. Therefore, our assumption into that p is a composite integer is wrong. Hence, p is a prime number. Proved. Now we prove the next theorem. Theorem is, let p is a prime number and k is a positive integer, then phi p to the power k equal to p to the power k minus p to the power k minus 1 equal to p to the power k under bracket 1 minus 1 by p. Now we prove this. Given that p is a prime number, phi p to the power k equal to Euler's phi function of p to the power k. Therefore, phi p to the power k equal to number of positive integers not exceeding p to the power k and they are relatively prime. To p to the power k. Since number of positive integer not exceeding p to the power k be p to the power k. p to the power k minus number of positive integers not exceeding p to the power k and they are not relatively prime to p to the power k. Let this is number 1. Since positive integers not exceeding p to the power k and they are not relatively prime to p to the power k be 1 multiply p, 2 multiply p, 3 multiply p, dot 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 p to the power k minus 1 multiply p. Therefore, number of these integers equal to 1, 2, 3 dot 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 p to the power k minus 1. This is number 2. Putting the value of 2 in 1, we get phi p to the power k equal to p to the power k minus p to the power k minus 1. This equal to common p to the power k 1 minus 1 by p. Proved. Now, with the help of the formula Euler's phi function, phi p to the power k equal to p to the power k under bracket 1 minus 1 by p. P is a prime number. We solve some problems. Number 1, phi 16. We may write this as phi 16 equal to phi 2 to the power 4. 2 is a prime number. This equal to 2 to the power 4, 1 minus 1 by 2. This equal to 2 to the power 4 multiply half. equal to 2 cube equal to 8. Number 2. Find phi 25. This equal to phi 5 square. 5 is a prime number. And this will be equal to 5 square multiply 1 minus 1 by 5. This equal to 5 square multiply 4 by 5. This equal to 5 multiply 4 equal to 20. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.